The following lecture are based on the material that can be found with the Wikipedia site, the free encyclopedia there at this site, and the instructor appreciate for their materials for this lecture. And the Wikipedia material will cover these contents. I'm going down slowly. Material that I'll be using for this lecture. The second material that I'll be referring in making this video for lecture for building tubular structure is based on paper called Shellac in Tube Structures. And this paper can be also found with this YouTube address and internet address, and their authors right here. This gentleman and this gentleman or lady, and the author of this paper are really appreciated, and they're providing a intuition for making this video lecture. Thank you very much. Okay, let's review design of tall building structures using tubular frames. Here we have two cases of tubular frames in which we have 100% perfect shear strength for spandrel girders. So where we have a linear transformation of the load from flange side, tension flange side to compression flange side, tension flange side to compression flange side, so that your column load on web frame follows linear, so that your distribution of transferred load on web frames looks like you're following strength compatibilities. So, and also your compression distribution on compression flange follows uniform distributions, as you see over there. So when you have a perfect 100% perfect shear strength for spandrel girders here and here, whereas your load do not follow straight line, as you see here. Your load on web frame follows a curve that is reduced from the straight line, as you see over here. So curve reduced from the straight line here and here as well. When you have the shear strength for girders and beams not sufficient to transfer your load from tension phase to compression phase. And also, if you see here, compression phase of the building, your load distribution is not perfectly uniform. It is very non-uniform, so that the column in middle here do not pick up the actual forces that picked up by these columns, resulting in the columns here not working as hard as those columns here and here, which is very hard working. This does not represent good design, as you can see right there. See, so it is very important how we're gonna provide very good shear strength for spandrel girders, both in web side and compression force side, so that we have a linear transfer mechanism and uniform transfer mechanism for both web frame and flange frames, and eliminating this type of transfer mechanism. So we have two ways of achieving 100% shear strength for girders. The first one is that we can space your columns here as close as possible, so that you can provide a good shear strength for spandrel girders. And second way is again that your shear strength for spandrel girders should be enough, sufficient. Okay, so two things. One, you have to install your column as close as possible, and also you have to provide your shear strength for spandrel girders as much as possible, sufficient to provide a straight distributions for web face of the frame and compression face of the frames. So I am explaining one more time, looking at this class here, building frames. You're having a lateral load in this direction, to the left, to right, and if you have a perfect shear strength for girders and beams, you will have a straight line here, straight line distribution. So it is a based on perfect shear strength of girders. If you don't have enough shear strength for girders, then you will have a shear lags. This is called shear lags. This is called shear lag phenomenon, as we learned. So here you have a shear lags, and this is called positive shear lag, and this is called negative shear lag. But mostly we have positive shear lag when you don't have enough shear strength for girders. Okay. And you have a same distribution of vertical load of column in compression phase if you have a perfect shear deformations, perfect shear stiffness for girders, so the shear deformations can be prevented. Then you have your straight line distributions, no shear lags. And here, if you have no shear lags, then you have a straight line in this line, right? Okay, it looks like a strain compatibility lines here, so that actual load is proportional to the distance from the neutral axis. You have neutral axis right here. So I may plot the neutral axis here, not here, and you have a neutral axis here as well. You put lateral load that directions. And if you have a shear lag, then you have positive shear lag for this line and negative shear lag for this line. So this is the actual stress distribution in flange frames or flange walls. One of these. And same here, actual stress distribution in web frames or walls. One of these, depending on the shear strength of the spandrel girders and spandrel beams. Okay, this is very important, and I hope you understand this mechanism by now. Of course, when you have lateral load this way, this will be a tension column load here, compression column load. Right? This is tension phase, compression phase. Okay, this figure shows the orthotropic panels of tubular structures, and this is flange. you can have a load this direction, you can have load this directions, and whereas you have a web frames. So whole tubular shapes is used as a building resisting frames for high-rise buildings. And this is a frame tubular building schematic plan view. And as you see here, this is columns spaced closely in order to provide this is spandrel beams and girders here. This is spandrel girders and beams right there. Same here, right? This is beams and girders. This is columns, as you see. This is columns. So the column should be spaced close enough. All columns spaced close enough so that your spandrel beams here, your spandrel beams in between columns can have a shear strength enough to prevent shear lag phenomena from occurring, from happening. So now it is very clear how important it is that you have enough shear strength for columns and girders. And this is a concrete floor framings and it is a closely spaced perimeter columns here all the way, and it is a deep spandrel beams. And we still have a interior columns. We can have a tube inside again here, tube inside, and this is core. So we may have multiple tubes here, exterior tubes, and we have interior tubes here. So we call this type of structure tube in tube. Tube in tube. So you can design tube in tube, or you can design a bundle tube. Bundle tube, I explained that we have a straight frames across the building section here and here and here, same thing here, okay, here. Then we call this is a bundle tube. Okay? So this is how you can design tubular frames for resisting load for high-rise buildings, resisting loads for high-rise buildings. Okay, let's review one more time. This is a Sears Tower that is located in Chicago, United States. Look at that. Your bundle frame disappears here and disappears here, disappears here. One by one, it disappears as building goes high-rise part. So that you start 9 cells of tubular structure when you start at first level, and it drops out 2 and 2 here at 51 to 55 floors, and then another 2 cells here drops out 67 to 90 floors. Only 2 cells of tubular frames remains from 91 to 108 floors. So that if you go really in here and the 2 floors are very narrow, small at these floors, because all the other cells of frames were dropped out. So in this way, overall frame shapes looks like this. So this is how you can also design your tubular structure. So it explains by colors, frames that remains. This cell goes from here to here, whereas this frame cell goes from here to here, right? And so on and so forth. And if you take a look at it separating, and you have only two goes here, another two goes here, another three cells goes there, red cells go there. So this is a breakdown of tubular bundled tube structure of the Wills Tower with simplified floor frames. It is very interesting. So you can design this way in your projects. And what is the frames that goes all the way from the bottom to the top? This red frames. Red frame only starts from the bottom and goes all the way to top floors, whereas this blue cells drops out the earliest at 51 floor, right? And the green drops out a little higher, 67, and this drops out at around 91, and this survives all the way from the first floor to the last floor of the building. But this is very easy to understand how you can plan your vertical topology of the building, so that you can have a efficient lateral resisting structures, frames, using a tubular structures. Tubular structures are working independently, cell by cell, so you can drop it out as much as you want while it goes up. This is another tubular building called John Hancock Center in Chicago as well, designed in 1965 and finished 1969. And this is beautiful building constructed of tubular structures. And so this is Wills Tower, and formerly called Sears Tower. Wills Tower finished in 1973, introduced the bundle to structural design that I just explained, and it was the tallest building until 1998 for about 25 years. And this is bundle, right? You have 9 bundles here when you start at the first floor. This is a evolution of structural systems here, and we are talking here. This is a tubular bundle. Tubular is pretty good for tall buildings, and we have a exterior frame tube only. One frame as tube structures can still go up until around 90, whereas the bundle tube can go up until around 110, and this is also exterior diagonalized tube. You have a tube but with a mega diagonal truss at exterior face, something like this. This is a mega truss that is installed. Exterior face of the tubular structure can bring your building very high, up until over 100 stories. We have here outriggers, and this is a frame with a shear wall structure. We don't have anything but core walls and shear walls and trusses and frames, something like a dual frames. Still can cover 40 stories, and we have only rigid frames can cover 30s, and rigid, semi-rigid frames can cover 15 to 10 and floor. So we can start with a semi-rigid covers 15, rigid covers 30, and frame with shear truss can cover a 45, and you can cover up to the 60 floors if you add a outrigger frames and belt trusses frame with shear band and outrigger trusses. So we learned this as a outrigger frames and belt trusses and cap trusses. It can go up until the 60 floors if you see here. And then we have another mega columns and mega walls, also pretty good to resist the high-rise rows up until 60 floors. And we learned this tubular, exterior tubular and bundle tubular, exterior tubular with a mega trusses and cover one of the highest buildings in the building history. Okay, concludes that this we have a serious shear lag phenomenon here, not linear, right? And we can put further interior frames that cross the building sections that we can reduce shear lag phenomenon. How? We can increase the spandrel beams shear capacity as well. Also, we can provide a direct loading path from here to here. If this is tension phase, your loading can go and transfer into the columns on compression phase directly, indirectly, so that we have a uniform distribution of the load here, and we have a straight line distribution for web frames. And this is a uniform distribution on compression flange frames. And this is a good design, right? This is very good design. So we have loadings right there, wind loadings, and this is tensile stresses. It can go many ways, and these columns will transfer its loads through this frame line, and this column will transfer its load through this frame line, and this column through its own frames, and this column will have its own loading paths. All loading paths, all separate independent loading paths are provided so that the column side here in compression phase receives very good compression loads without losing it. So your distribution here of uniformity will be received with the same uniform distributions at the other side for compressions. So that it is very easy for you to separate your frames into some subframes for tubular structure. We call this bundled tube, right? Each of them can also drop out as the building goes up, right? And if you have enough bundle system with enough loading paths, independent loading paths, you can also have a straight line load distributions for web frames. He says you're 4 to 6 meter typical between columns. I say 3 to 5 and 4 to 6. And this column spacing can be determined as a trial and error technique. So you try 3 meter, 4 meter, 5, 6, 7, whatever to try pick the load from the computer output, from all the columns, and then try to see the distribution on flange frames and web frame. Then you will decide whether you have the column space which is close enough to prevent a shear lag phenomenon. All right.